Right now, as you watch this, a silent revolution is unfolding a billion light years away. Astronomers are staring at a patch of sky so small it could be covered by a grain of sand held at arm's length, and yet, in that tiny sliver of darkness, they have found something that defies every rule we thought the universe obeyed. This is the story of MOM Z14, a galaxy so ancient, so luminous, and so impossibly complex that its very existence threatens to unravel the fabric of modern cosmology. If you think the universe is a place of order and predictability, prepare to have your mind changed. Because MOM Z14 is the galaxy that should not exist. Let's set the stage. For decades, astronomers have believed they understood how galaxies form and grow. After the Big Bang, the universe was a hot, dense soup of particles. As it expanded and cooled, tiny fluctuations in density, quantum ripples stretched across space, became the seeds of structure. Gravity pulled matter together, forming the first stars, then small galaxies, which merged over billions of years to create the grand spirals and ellipticals we see today. The early universe, we were told, was a place of darkness and simplicity. Galaxies were supposed to be small, faint, and chaotic, mere building blocks, not finished masterpieces. But then came the James Webb Space Telescope, a machine so powerful it can see back in time to the first few 100 million years after the Big Bang. Its golden mirrors, floating 1,000,000 miles from Earth, are tuned to the faint glow of the most distant galaxies. And in its first deep-field images, astronomers spotted something that made them question everything a galaxy catalogued as MOM Z14, shining with the light of billions of stars, already massive and organized when the universe was less than 300 million years old. Pause for a moment and let that sink in. The universe is 13.8 billion years old. MOM Z14 existed when the cosmos was just 2% of its current age. According to every simulation, every theory, every textbook, there simply wasn't enough time for a galaxy like this to form. It's as if you walked into a hospital nursery and found a fully grown adult reading a newspaper among the newborns. The rules say it can't happen, and yet there it is. What makes MOM 14 so extraordinary? First, its brightness. This galaxy is not a faint smudge barely distinguishable from the cosmic background. It blazes with the energy of countless young, hot stars. Its light has traveled for more than 13 billion years, stretched and reddened by the expansion of space. Yet it still outshines galaxies that are billions of years older. Second, its size. MOM Z14 is not a tiny, primitive clump. It spans thousands of light years, with a structure that hints at spiral arms and a dense, star-forming core. Third, its maturity. The stars in MOM Z14 are not all newborns. Some show signs of having already lived and died, enriching the galaxy with heavy elements, carbon, oxygen, iron, that should have taken hundreds of millions of years to accumulate. The discovery sent shockwaves through the astronomical community. Teams around the world scrambled to confirm the data. Was it a mistake? A trick of the telescope? A foreground object masquerading as a distant galaxy? But every test, every analysis, pointed to the same conclusion: MOM Z14 is real, and it is ancient. To understand why this is such a problem, we need to talk about the cosmic timeline. After the Big Bang, the universe was a hot plasma of protons, neutrons, and electrons. It took 380,000 years for atoms to form and the universe to become transparent. For the next 100 million years, darkness reigned, the so-called cosmic dark ages. Then, the first stars ignited, flooding the universe with light and beginning the process of reionization. Galaxies began to assemble, but slowly. The earliest ones, according to theory, should have been small and dim, their growth limited by the trickle of available gas and the violence of supernova explosions. But MOM Z14 breaks this narrative. its mass rivals that of the Milky Way, a galaxy that took billions of years to reach its current size. Its star formation rate is off the charts, producing new suns at a pace that seems physically impossible. And its chemical makeup suggests that several generations of stars have already lived and died, polluting the interstellar medium with the elements needed for planets and perhaps even life. How could this happen? How could a galaxy so massive, so bright, so mature, exist at a time when the universe was barely out of its infancy? Theories began to crumble. Some astronomers suggested that the laws of physics might be different in the early universe. Others proposed exotic forms of dark matter or new mechanisms for rapid star formation. A few even whispered about the possibility of new physics, unknown forces or particles that could accelerate the growth of structure. But for now, there are more questions than answers. ZW14 stands as a cosmic anomaly, a challenge to our understanding of how the universe works. It is a reminder that, for all our knowledge, the cosmos still holds secrets that can astonish and confound us. And this is just the beginning. In the next section, we'll dive deeper into the discovery of Z14, how it was found, what makes it unique, and why it has become the most controversial object in modern astronomy. We'll meet the scientists who first glimpsed its light, and explore the cutting-edge technology that made this discovery possible. Because to understand why Z14 should not exist, we first need to see it through the eyes of those who found it. The story of Z14's discovery begins not with a single eureka moment, but with a painstaking search through the deepest reaches of the cosmos. In the months after the James Webb Space Telescope began its science operations, astronomers around the world were racing to analyze its first images. These were not ordinary photographs. Each pixel in a Webb deep field represents light that has traveled for billions of years, carrying with it the history of the universe itself. Teams sifted through these images, looking for the faintest, reddest smudges, signatures of galaxies from the dawn of time. It was in one such image, a patch of sky no larger than a thumbnail, that a group of researchers noticed something odd. Amid the expected scatter of dim, irregular galaxies, there was a single brilliant point, Z14. At first, it seemed too bright, too well defined, to be real. The team checked and rechecked their data, ruling out cosmic rays, instrumental glitches, and foreground stars. The object persisted. Its color, its spectrum, its position, all pointed to an extraordinary conclusion. This was a galaxy from the earliest epoch, shining with impossible intensity. The confirmation process was grueling. Astronomers used Webb's powerful spectrographs to split the galaxy's light into its component wavelengths, searching for the telltale fingerprints of hydrogen, oxygen, and other elements. The redshift measurement was unambiguous. Z14's light had been stretched by a factor of more than 14, placing it just 290 million years after the Big Bang. This was not a case of mistaken identity. The galaxy was real, and it was ancient. The news spread quickly through the scientific community. Some were skeptical, suspecting a trick of gravitational lensing, a foreground cluster magnifying a more ordinary galaxy. But careful analysis showed no evidence of lensing. Others wondered if the object might be a rare type of quasar, powered by a supermassive black hole. But Z14's spectrum lacked the characteristic emission lines of an active galactic nucleus. It was, by all accounts, a galaxy, a collection of stars, gas, and dust, assembled impossibly early. The implications were staggering. For decades, the standard model of cosmology had predicted a slow, orderly buildup of structure. Small galaxies formed first, merging over time to create larger systems. The process was thought to be limited by the cooling of gas, the feedback from supernovae, and the gradual accumulation of dark matter. MOM Z14 shattered these expectations. Its mass, its luminosity, its chemical complexity, all pointed to a galaxy that had somehow leapfrogged the normal stages of evolution. The discovery forced astronomers to confront uncomfortable questions. Was MOM Z14 a freak, a 1 in a billion outlier? Or was it the tip of an iceberg, evidence that the early universe was far more active and chaotic than anyone had imagined? As more Webb data poured in, hints of other massive, bright galaxies began to emerge. MOM Z14 was not alone. The cosmic dawn, it seemed, was ablaze with activity. To appreciate the magnitude of this discovery, it helps to understand the tools that made it possible. The James Webb Space Telescope is the most ambitious astronomical instrument ever built. Its 6.5-meter mirror, coated in gold, is designed to capture the faintest whispers of infrared light. Its instruments are cooled to just a few degrees above absolute zero, allowing it to see through the dust and gas that obscure the earliest galaxies. Webb's position, 1,000,000 miles from Earth at the second Lagrange point, keeps it shielded from the heat and light of our planet, giving it an unobstructed view of the cosmos. But technology alone is not enough. The discovery of MOM Z14 was the result of years of planning, collaboration, and ingenuity. Teams of scientists designed surveys to maximize the chances of finding the most distant galaxies. They developed algorithms to sift through terabytes of data, flagging candidates for follow-up observations. And when the first hints of MOM Z14 appeared, they mobilized quickly, securing precious telescope time to confirm its nature. The human element is often overlooked in stories of scientific discovery, but it is essential. The astronomers who found MOM Z14 were not just technicians operating a machine. They were explorers, driven by curiosity and a sense of wonder. Many had spent their careers searching for the first galaxies, enduring years of false starts and dead ends. The moment they realized what they had found, a galaxy that should not exist, was a moment of awe, disbelief, and exhilaration. Yet, with discovery comes responsibility. The team knew that extraordinary claims require extraordinary evidence. They opened their data to scrutiny, inviting colleagues to test and challenge their results. The debates were fierce, the analysis meticulous. In the end, the evidence held. MOM Z14 was real, and its existence demanded an explanation. As the news broke, the world took notice. Headlines proclaimed the discovery of a forbidden galaxy, a cosmic anomaly, a challenge to the Big Bang. The public, captivated by the idea of a galaxy that defied the rules, flocked to images and animations of MOM Z14. For a brief moment, the mysteries of the early universe became front-page news. But for astronomers, the discovery was just the beginning. MOM Z14 was not merely a curiosity, it was a clue, a signpost pointing toward new physics, new processes, and perhaps a new understanding of the cosmos itself. The search for answers had only just begun. To truly grasp why MOM Z14 is so confounding, we need to step back and examine the cosmic rules it appears to break. For decades, astronomers have relied on a well-tested framework to explain how galaxies form and evolve. This framework, known as the Lambda Cold Dark Matter Model, or ЛCDM, has been the backbone of cosmology. It describes a universe dominated by dark energy and dark matter, where ordinary matter, stars, gas, dust, makes up only a small fraction of the total. In this model, structure forms hierarchically. Small clumps of dark matter merge to create larger halos, which then attract gas, cool, and ignite the first stars. Over billions of years, these halos merge, galaxies grow, and the universe becomes the tapestry of light we see today. But MOM Z14 doesn't fit. According to ΛCDM, there simply hasn't been enough time for a galaxy of its mass and brightness to assemble. The early universe was a hostile place. Gas was hot. The cosmic microwave background still glowed with residual heat from the Big Bang, and the first stars, population 3 stars, were massive, short-lived, and violent. Their supernova blasted the surrounding gas, making it difficult for new stars to form. The process of cooling, collapsing and building up a galaxy was supposed to be slow and gradual. Yet MOM Z14 is anything but slow and gradual. Its mass is estimated to be several billion times that of the Sun, rivaling galaxies that should have taken 1,000 times longer to form. Its star formation rate is staggering, producing new stars at a pace that outstrips even the most active galaxies in the modern universe. And its chemical composition is rich in heavy elements, carbon, oxygen, iron, suggesting that multiple generations of stars have already lived and died within its boundaries. This is where the contrast becomes stark. In the standard picture, the first galaxies were supposed to be small, dim, and primitive. They were the cosmic seeds, destined to merge and grow over eons. MOM Z14, by contrast, is a fully formed giant, blazing with the light of billions of stars, organized and mature at an age when the universe was still in its infancy. It's as if you found a skyscraper in a village of huts, built overnight with no blueprint. The implications ripple outward. If MOM Z14 exists, then either our understanding of galaxy formation is incomplete, or the early universe was far more efficient at building structure than we thought. Some theorists have proposed that the initial conditions after the Big Bang were not as smooth as assumed. Perhaps there were regions of higher density, cosmic hotspots, where matter collapsed more quickly, giving rise to massive galaxies like MOM Z14. Others suggest that dark matter itself might behave differently in the early universe, clumping more rapidly or interacting in ways we have yet to discover. There are even more radical ideas. Some physicists have speculated that the laws of physics themselves might have been different in the first few 100 million years. Could the strength of gravity, the behavior of dark energy, or the properties of fundamental particles have changed over time? If so, the consequences would be profound, not just for astronomy but for our entire understanding of reality. But before we rewrite the textbooks, scientists are careful to consider more mundane explanations. Could MOM Z14 be an illusion, a trick of perspective or measurement? Astronomers have scrutinized the data, looking for signs of gravitational lensing, a foreground cluster magnifying a more ordinary galaxy. But the evidence for lensing is weak. The galaxy's spectrum, its redshift, its position in the sky, all point to a genuine, distant object. Another possibility is that MOM Z14 is not a single galaxy, but a merger of several smaller systems caught in the act of coalescing. High-resolution images from Webb show hints of clumps and irregularities, but the overall structure is surprisingly smooth and organized. If it is a merger, it is an unusually advanced one, with star formation already in full swing. The debate is ongoing, but one thing is clear. MOM Z14 is forcing astronomers to rethink their assumptions. It is a cosmic puzzle, a challenge to the status quo, and a beacon for new ideas. In the halls of observatories and the pages of scientific journals, the question echoes, how did this galaxy come to be? As we search for answers, MOM Z14 is not alone. Webb and other telescopes are finding more and more examples of massive, bright galaxies at extreme distances. The early universe, once thought to be a quiet, dark place, is now revealed as a bustling, dynamic environment filled with surprises. Each new discovery adds to the sense of wonder and the sense of mystery. In the next section, we'll explore the possible origins of MOM Z14. What processes could have created such a galaxy so quickly? Are there hidden forces at work, Or is nature simply more creative than we imagined? We'll dive into the latest theories, the cutting-edge simulations, and the bold ideas that are reshaping our view of the cosmic dawn. To unravel the mystery of MOM Z14's origins, astronomers have turned to the most advanced simulations and theoretical models available. These digital universes, running on supercomputers, attempt to recreate the conditions of the early cosmos, tracking the evolution of matter from the first moments after the Big Bang to the formation of galaxies and stars. In these simulations, the rules of physics are encoded: gravity, gas dynamics, radiation, chemistry, and the elusive effects of dark matter and dark energy. By tweaking the initial conditions and physical laws, scientists can test different scenarios and see which ones produce galaxies like MOM Z14. The first and most straightforward explanation is that MOM Z14 formed in a region of the universe that was unusually dense. In the aftermath of the Big Bang, matter was not distributed perfectly evenly. Tiny fluctuations, quantum ripples magnified by cosmic inflation, created pockets where gravity could work more quickly. If MOM Z14's birthplace was one of these rare, high-density regions, it could have collapsed faster, pulling in gas and dark matter at a breakneck pace. This would allow for rapid star formation and the early assembly of a massive galaxy. But even in the densest regions, simulations struggle to produce a galaxy as large and luminous as MOM Z14 in such a short time. The bottleneck is cooling gas must shed its heat before it can collapse to form stars. In the early universe, with few heavy elements to aid in cooling, this process should have been slow. Yet, MOM Z14's spectrum shows evidence of significant chemical enrichment: carbon, oxygen, and iron, implying that several generations of stars have already lived and died, seeding the galaxy with the elements needed for efficient cooling and further star formation. This leads to a second possibility. MOM Z14 experienced a burst of hyper-efficient star formation, perhaps triggered by a series of rapid mergers. In this scenario, smaller protogalaxies collided and merged, compressing gas and igniting waves of starbirth. The resulting supernovae would enrich the gas with heavy elements, accelerating the cooling process and allowing even more stars to form. This runaway feedback loop could, in theory, build a massive, mature galaxy in record time. However, there are limits to how fast this process can go. Supernova explosions also inject energy into the surrounding gas, heating it and blowing it out of the galaxy. This feedback is thought to regulate star formation, preventing galaxies from growing too quickly. For MOM Z14 to reach its observed mass and brightness, either the feedback was weaker than expected, or the inflow of fresh gas was so overwhelming that it overcame the effects of supernova-driven winds. A third, more exotic idea is that the first stars, population Aether stars, were far more massive and short-lived than previously thought. These primordial giants could have lived fast and died young, exploding as supernovae and enriching their surroundings with heavy elements in just a few million years. If MOM Z14 formed in a region with an unusually high concentration of these stars, it could have started the process of galaxy assembly, creating a mature system almost overnight. Some theorists have even proposed that dark matter itself might play a more active role. In the standard model, dark matter is cold and collisionless, interacting only through gravity. But what if, in the early universe, dark matter could clump or interact in ways we have not yet observed? If dark matter halos formed more quickly or were more efficient at pulling in gas, they could provide the gravitational wells needed to build massive galaxies like MOM Z14. There are also ideas that push the boundaries of known physics. Could the strength of gravity have been different in the early universe? Could there be unknown particles or forces that accelerate the collapse of matter? While these ideas are speculative, the existence of MOM Z14 gives them new urgency. When observations defy expectations, science must be willing to entertain bold possibilities. Yet, for all these theories, there is still no consensus. Each explanation has its strengths and weaknesses, and none can fully account for all the observed properties of MOM Z14. The galaxy remains an outlier, a challenge to our understanding, and a catalyst for new ideas. What is certain is that MOM Z14 is not alone. As Webb continues to scan the sky, more galaxies like it are being discovered, massive, bright, and mature, existing at times when the universe was supposed to be dark and simple. The cosmic dawn, once thought to be a slow and gentle awakening, is now revealed as a period of frenetic activity, with galaxies forming, merging, and evolving at a pace that defies our models. In the next section, we'll shift our focus to the evidence itself. What do the observations of MOM Z14 actually show? How do astronomers measure its distance, its mass, its star formation rate, and its chemical composition? We'll go behind the scenes of the data, exploring the techniques and technologies that allow us to peer across billions of light years and reconstruct the history of a galaxy that should not exist. Peering into the depths of the universe to study a galaxy like MOM Z14 is a feat of both technology and ingenuity. The light we see from this galaxy began its journey more than 13 billion years ago, long before our solar system even existed. By the time it reaches us, it is stretched and dimmed by the expansion of space, arriving as faint infrared photons. Detecting and analyzing this ancient light requires instruments of extraordinary sensitivity and precision, none more so than the James Webb Space Telescope. The first step in studying MOM Z14 was simply finding it. Webb's deep field surveys are designed to capture the faintest, most distant galaxies by staring at a single patch of sky for dozens of hours. Each exposure collects photons that have traveled across cosmic time, building up an image that reveals the universe as it was billions of years ago. In these images, most galaxies appear as tiny, red smudges, evidence of their great distance and the redshift caused by the universe's expansion. MOM Z14, however, stood out immediately. Its brightness and color marked it as a candidate for one of the most distant galaxies ever observed. To confirm its distance, astronomers turned to spectroscopy. By splitting the galaxy's light into its component wavelengths, they could search for specific features, emission and absorption lines, that act as cosmic fingerprints. The most important of these is the Lyman alpha line, produced by hydrogen atoms. In nearby galaxies, this line appears in the ultraviolet, but for MOM Z14, the line is shifted deep into the infrared, a clear sign that its light has been stretched by a factor of more than 14. This redshift, denoted as Z14, places the galaxy just 290 million years after the Big Bang. But distance is only the beginning. To understand MOM Z14's true nature, astronomers needed to measure its mass, its rate of star formation, and its chemical composition. This is where Webb's suite of instruments shines. By analyzing the galaxy's spectrum, scientists can estimate the total amount of starlight, which in turn reveals the mass of stars present. For MOM Z14, the numbers are staggering: billions of solar masses, assembled in a cosmic blink of an eye. The spectrum also reveals the rate at which new stars are forming. Young, hot stars emit copious amounts of ultraviolet light, which is absorbed by surrounding gas, and re-emitted at specific wavelengths. By measuring the strength of these emission lines, astronomers can estimate how many new stars are being born each year. MOM Z14's star formation rate is among the highest ever observed, rivaling or exceeding that of much larger, older galaxies. Perhaps most surprising is the evidence for chemical enrichment. The first stars in the universe were made almost entirely of hydrogen and helium, with virtually no heavier elements. These so-called population Earth stars lived fast and died young, exploding as supernovae and seeding their surroundings with carbon, oxygen, and iron. The presence of these elements in MOM Z14's spectrum indicates that several generations of stars have already lived and died, enriching the galaxy's gas and enabling the formation of planets and, potentially, life. But how reliable are these measurements? Astronomers are acutely aware of the challenges involved in studying such distant objects. The faintness of the light, the effects of cosmic dust, and the limitations of current models all introduce uncertainties. To address these, scientists use multiple, independent methods to cross-check their results. They compare the observed properties of MOM Z14 with those of other distant galaxies, run simulations to test different scenarios, and use statistical techniques to estimate the likelihood of various outcomes. One of the most powerful tools in this effort is gravitational lensing. Occasionally, a massive cluster of galaxies lies between us and a distant object, bending and magnifying its light like a cosmic lens. While MOM Z14 does not appear to be strongly lensed, astronomers use lensing in other cases to study galaxies that would otherwise be too faint to detect. This technique has revealed a population of massive, bright galaxies at extreme distances, suggesting that MOM Z14 is not a lone outlier, but part of a broader trend. The data from Webb is also complemented by observations from other telescopes. Ground-based observatories, such as the Atacama Large Millimeter-Submillimeter Array, can detect the cold gas and dust in distant galaxies, providing additional clues about their structure and evolution. Together, these instruments paint a picture of MOM Z14 as a galaxy that is not only massive and bright, but also complex and dynamic, with ongoing star formation and a rich chemical history. The process of analyzing this data is painstaking. Teams of astronomers spend months, sometimes years, extracting every bit of information from the faint signals. They debate interpretations, refine models, and publish results for the community to scrutinize. The stakes are high as a single error could overturn the conclusions, while a robust result could reshape our understanding of the universe. Yet, for all the challenges, the evidence for MOM Z14's extraordinary nature continues to mount. Each new observation, each new analysis, adds to the sense of wonder, and the sense of mystery. How could such a galaxy form so quickly? What does it tell us about the early universe? And what other surprises await us as we peer ever deeper into the cosmic past? In the next section, we'll explore the broader implications of MOM Z14's discovery. How does it fit into the emerging picture of the early universe? What does it mean for our theories of galaxy formation, dark matter, and cosmic evolution? And how are scientists responding to the challenge it presents? The answers may change the way we see the universe, and our place within it. The discovery of MOM Z14 has sent ripples through the entire field of cosmology, forcing scientists to re-examine some of their most cherished assumptions about the early universe. For decades, the prevailing view was that the first billion years after the Big Bang were a time of gradual, almost hesitant, cosmic awakening. Galaxies were thought to emerge slowly, their growth throttled by the scarcity of heavy elements and the violence of the first supernovae. The universe in this view was a place of darkness and simplicity, with complexity and brilliance reserved for later epochs. But MOM Z14, along with a growing list of similarly ancient and massive galaxies, has appended this narrative. Instead of a slow dawn, the early universe now appears to have been ablaze with activity. Galaxies like MOM Z14 were already forming stars at prodigious rates, assembling vast reservoirs of mass and enriching their surroundings with the elements needed for future generations of stars and planets. The cosmic dark ages, it seems, were shorter and less absolute than once believed. This new picture has profound implications for our understanding of galaxy formation. If galaxies could grow so large, so quickly, then the processes driving their assembly must be far more efficient than previously thought. Theories that once seemed secure are now under intense scrutiny. For example, the role of dark matter, the invisible scaffolding that shapes the growth of structure, may need to be reconsidered. If dark matter halos can collapse and merge more rapidly, or if their properties change under extreme conditions, this could help explain the existence of galaxies like MOM 14. Similarly, the feedback mechanisms that regulate star formation are being re-evaluated. In the Standard Model, supernova explosions and the winds from massive stars inject energy into the surrounding gas, heating it and driving it out of the galaxy. This feedback is thought to prevent runaway star formation, keeping galaxies from growing too quickly. But MOM Z14's high star formation rate suggests that either feedback was less effective in the early universe, or that the inflow of fresh gas was so overwhelming that it simply outpaced the effects of supernovae and stellar winds. The chemical enrichment of MOM Z14 also raises questions. The presence of heavy elements implies that several generations of stars have already lived and died, polluting the galaxy's gas with the building blocks of planets and life. This process, known as nucleosynthesis, was supposed to take hundreds of millions of years. Yet in MOM Z14, it appears to have happened in a fraction of that time. This suggests that the first stars, population of 30 stars, may have been even more massive and short-lived than previously thought, exploding as supernovae and enriching their surroundings almost immediately. The implications extend beyond galaxy formation. The existence of MOM Z14 challenges our understanding of cosmic reionization, the process by which the first stars and galaxies ionized the hydrogen gas that filled the universe, making it transparent to light. If galaxies like MOM Z14 were common, they could have produced enough ultraviolet radiation to reionize the universe much earlier than expected. This would have profound consequences for the timeline of cosmic history, affecting everything from the formation of the first black holes to the growth of large-scale structure. The discovery has also sparked a flurry of activity among theorists. New models are being developed to explain how galaxies like MOM Z14 could form so quickly. Some propose that the initial conditions of the universe were more varied than previously thought, with regions of extreme density acting as cosmic nurseries for rapid galaxy formation. Others suggest that dark matter may have properties that allow it to clump and collapse more efficiently in the early universe. Still others are exploring the possibility of new physics, unknown forces or particles, that could accelerate the growth of structure. At the same time, observers are redoubling their efforts to find more galaxies like MOM Z14. The James Webb Space Telescope is just beginning its mission, and each new deep-field image has the potential to reveal additional surprises. Ground-based telescopes, equipped with advanced spectrographs and adaptive optics, are also joining the hunt, probing the universe at ever greater distances and with ever finer detail. The response from the scientific community has been a mix of excitement, skepticism, and determination. Some researchers caution that extraordinary claims require extraordinary evidence, and that more data is needed to confirm the true nature of MOM Z14 and its peers. Others see the discovery as a once-in-a-generation opportunity to push the boundaries of knowledge, to test the limits of current theories, and to explore new frontiers in physics and astronomy. What is clear is that MOM Z14 has become a touchstone for the next era of cosmic discovery. Its existence demands explanation, and in seeking that explanation, scientists are being forced to confront the deepest questions about the universe. How did the first galaxies form? What are the true properties of dark matter and dark energy? Are the laws of physics truly universal, or do they change under extreme conditions? And, perhaps most tantalizing of all, what other wonders await us in the unexplored depths of cosmic time? In the next section, we'll take a closer look at the people behind the discovery, the astronomers, engineers, and visionaries whose work made it possible to find and study a galaxy that should not exist. Their stories, their challenges, and their triumphs are as much a part of this cosmic mystery as the galaxy itself. Behind every cosmic discovery lies a tapestry of human effort, of visionaries who dared to dream, engineers who turned dreams into reality, and scientists who devoted years to the pursuit of knowledge. The story of MOM Z14 is not just about a distant galaxy. It is also about the people who made its discovery possible, each playing a vital role in unraveling one of the universe's greatest mysteries. It begins with the architects of the James Webb Space Telescope, a project that spanned more than 2 decades and involved thousands of individuals from around the globe. Engineers faced daunting challenges. Building a mirror large enough to collect the faintest light, designing instruments sensitive enough to detect the earliest galaxies, and creating a sunshield the size of a tennis court to keep the telescope cold and stable. Every component had to survive the rigors of launch, and then unfold perfectly in the vacuum of space, a million miles from home. The margin for error was razor thin. For years, setbacks and delays threatened to derail the mission. But the team persevered, driven by the promise of peering deeper into the universe than ever before. When Webb finally launched, the astronomical community held its collective breath. The deployment sequence was a ballad of precision, with hundreds of moving parts working in concert. As the first images arrived, relief gave way to awe. The telescope was performing beyond expectations, revealing a universe teeming with detail and complexity. Among the scientists eagerly awaiting these images were the teams dedicated to studying the cosmic dawn, the epoch when the first galaxies emerged from darkness. For these astronomers, the search for ancient galaxies was both a technical and intellectual challenge. They designed surveys to maximize the chances of finding the most distant objects, developed algorithms to sift through mountains of data, and built models to interpret the faint signals from the edge of time. The discovery of MOM Z14 was the result of this meticulous preparation. When the galaxy first appeared in the data, it was flagged as a candidate for follow-up observations. The team worked around the clock, analyzing its spectrum, measuring its redshift, and comparing its properties to those of other distant galaxies. The excitement was palpable, but so was the skepticism. The team knew that extraordinary claims would be met with scrutiny. They double and triple checked their results, consulted with colleagues, and subjected their findings to rigorous peer review. The process was intense, with debates over every detail. Was the redshift measurement accurate? Could the galaxy be a foreground object or a lensed image? Was there any chance of a data artifact? Only after every alternative had been ruled out did the team announce their discovery to the world. The response was electric. News of MOM Z14's existence spread quickly, capturing the imagination of scientists and the public alike. For the astronomers involved, it was a moment of triumph, a validation of years of hard work and a testament to the power of human curiosity. But it was also a moment of humility. The universe had revealed something unexpected, a reminder that nature is always more creative than we imagine. The story does not end with the discovery. The team continues to study MOM Z14, seeking to understand its structure, its history, and its place in the cosmic web. They collaborate with theorists, sharing data and insights, and with engineers, pushing the limits of what telescopes and instruments can achieve. Their work is part of a global effort, with scientists from every continent contributing to the quest to understand the universe's earliest epochs. Beyond the scientists, there are countless others whose contributions made the discovery possible: the technicians who assembled the telescope, the programmers who wrote the software, the mission planners who coordinated observations, and the educators who share these discoveries with the world. Each played a role in bringing MOM Z14 into the light. The human story of MOM Z14 is one of perseverance, collaboration, and wonder. It is a story of people who refused to accept the limits of current knowledge, who built tools to see the invisible, and who dared to ask the biggest questions. Their journey is ongoing, and with each new observation, they move closer to understanding not just how MOM Z14 came to be, but how the universe itself was born. In the next section, we'll return to the science, exploring how MOM Z14 fits into the larger tapestry of cosmic evolution. What does its discovery tell us about the formation of structure in the universe? How does it connect to the growth of black holes, the emergence of the cosmic web, and the birth of the first stars? The answers will take us from the smallest scales to the grandest structures, revealing the interconnectedness of all things in the cosmos. MOM Z14 is more than just an isolated marvel. It is a crucial piece in the grand puzzle of cosmic evolution. To understand its significance, we must place it within the broader context of how structure forms and grows in the universe. The story of MOM Z14 is, in many ways, the story of how the universe transformed from a nearly featureless expanse of primordial gas into the intricate web of galaxies, stars, and planets we see today. In the earliest moments after the Big Bang, the universe was astonishingly uniform. Tiny fluctuations in density, imprinted by quantum processes and magnified by cosmic inflation, served as the seeds for all future structure. Over time, gravity amplified these fluctuations, drawing matter together into filaments and nodes that would become the backbone of the cosmic web. Dark matter, invisible but dominant, provided the scaffolding upon which ordinary matter could gather and cool, eventually igniting the first stars. MOM Z14's existence at such an early epoch suggests that this process of structure formation was not only underway, but already remarkably advanced. The galaxy's mass and luminosity indicate that it sits at the intersection of several filaments in the cosmic web, a node where matter has pooled in abundance. This is not a random occurrence. Simulations show that the densest regions of the early universe are the first to collapse, forming the largest and brightest galaxies. MOM Z14, then, is likely a cosmic pioneer, one of the first great cities in a universe of emerging towns and villages. But the implications go further. The rapid assembly of MOM Z14 hints at a universe where the flow of gas along the cosmic web was both efficient and sustained. Cold streams of hydrogen and helium, funneled by gravity, could have fed the galaxy continuously, fueling its prodigious star formation. This process, known as cold accretion, is thought to be a key driver of early galaxy growth. In MOM Z14, we may be seeing this mechanism in action, operating at a scale and speed that challenges our models. The galaxy's chemical enrichment also ties it to the broader narrative of cosmic evolution. The first stars, massive, hot, and short-lived, produced the universe's first heavy elements in their fiery deaths. These elements, scattered by supernovae, mixed with the primordial gas, enabling the formation of new generations of stars and, eventually, planets. MOM Z14 spectrum rich in carbon, oxygen, and iron, is a testament to this cycle of birth, death, and rebirth. It is a snapshot of a universe rapidly becoming more complex, more hospitable to the chemistry of life. MOM Z14's place in the cosmic web also connects it to the growth of black holes. The centers of massive galaxies are often home to supermassive black holes, objects millions or billions of times the mass of the Sun. How these black holes form so quickly remains one of astronomy's great mysteries. The dense environment of MOM Z14, with its abundant gas and frequent mergers, could provide the perfect conditions for rapid black hole growth. If a massive black hole lurks at the heart of MOM Z14, it would offer vital clues about the interplay between galaxy formation and the birth of these cosmic giants. The discovery of MOM Z14 also informs our understanding of reionization, the epoch when the first galaxies and quasars flooded the universe with ultraviolet light, ionizing the hydrogen gas and ending the cosmic dark ages. Galaxies like MOM Z14, with their intense star formation, would have been major contributors to this process. Their light carved out bubbles of ionized gas, which grew and merged until the universe became transparent. By studying MOM Z14 and its peers, astronomers can reconstruct the timeline of reionization, shedding light on one of the most dramatic transitions in cosmic history. In this way, MOM Z14 is both a product and a driver of cosmic evolution. Its existence challenges our models, but it also provides a unique laboratory for testing new ideas. By studying its properties, its mass, its star formation, its chemical makeup, and its environment, scientists are piecing together the story of how the universe built its first great structures. In the next section, we'll delve into the mysteries that remain. What questions does MOM Z14 leave unanswered? What are the biggest puzzles facing astronomers as they try to explain its existence? And how might future observations and discoveries help resolve these cosmic enigmas? The journey of discovery is far from over, and the universe still holds many secrets waiting to be revealed. For all that MOM Z14 has revealed, it has also opened a Pandora's box of new questions, questions that reach to the very heart of cosmology and physics. Each answer seems to spawn more mysteries, and the galaxy's existence has become a rallying point for astronomers and theorists eager to probe the unknown. What, then, are the biggest puzzles that MOM Z14 presents, and how might we begin to solve them? First and foremost is the question of time. How could a galaxy so massive and mature exist when the universe was so young? The standard models of galaxy formation simply do not allow enough time for the processes of gas cooling, star formation, and chemical enrichment to operate at the scale observed in MOM Z14. If the timeline is correct, then something fundamental is missing from our understanding. Are there unknown mechanisms that can accelerate galaxy growth, or have we misjudged the conditions of the early universe? Closely related is the mystery of star formation. MOM Z14 star formation rate is not just high, it is extreme, rivaling or surpassing that of the most active galaxies in the modern universe. How did it sustain such a pace without being choked off by feedback from supernovae and stellar winds? Did the first stars behave differently, perhaps forming in clusters, or with a different initial mass function? Or was the inflow of cold gas so overwhelming that it simply drowned out the effects of feedback? The chemical composition of MOM Z14 is another enigma. The presence of heavy elements implies that several generations of stars have already lived and died, enriching the galaxy's gas in a cosmic blink of an eye. This rapid enrichment challenges our models of nucleosynthesis and chemical evolution. Did the first stars explode more violently, spreading their elements more efficiently? Or were there processes at work, perhaps involving black holes or exotic physics, that accelerated the mixing of elements? Then there is the question of black holes. If MOM Z14 harbors a supermassive black hole at its center, as many massive galaxies do, how did it grow so quickly? The formation of supermassive black holes in the early universe is a long-standing puzzle. Did they form from the direct collapse of massive gas clouds, bypassing the slow process of stellar evolution? Or did frequent mergers and abundant gas allow for rapid accretion and growth? MOM Z14 may hold the key to answering these questions. But for now, the evidence is tantalizing but incomplete. The environment of MOM Z14 also raises questions. Its position at a node in the cosmic web suggests that it benefited from a steady supply of cold gas, funneled along filaments by gravity. But how common are such environments in the early universe? Are galaxies like MOM Z14 rare outliers? Or are they the first examples of a previously hidden population? The answer will have profound implications for our understanding of cosmic structure and the distribution of matter in the universe. Perhaps the most profound mystery is whether the laws of physics themselves are truly universal. Some theorists have speculated that the early universe may have operated under different rules, perhaps with a stronger gravitational constant, or with dark matter behaving in unexpected ways. While there is no direct evidence for such changes, the existence of galaxies like MOM Z14 forces us to keep an open mind. Science advances by confronting anomalies, and MOM Z14 is a glaring anomaly. To address these questions, astronomers are planning a new generation of observations and experiments. The James Webb Space Telescope will continue to search for even more distant and massive galaxies, pushing the boundaries of the observable universe. Ground-based telescopes, equipped with ever more sensitive instruments, will probe the details of star formation, chemical enrichment, and black hole growth. Theoretical physicists are developing new models and simulations, testing ideas that once seemed far-fetched but now demand consideration. Collaboration will be key. The mystery of MOM Z14 is too big for any one team or discipline to solve alone. Astronomers, physicists, chemists, and computer scientists are joining forces, sharing data and insights, and challenging each other's assumptions. The search for answers is a global effort, driven by curiosity and the desire to understand our cosmic origins. In the next section, we'll look ahead to the future. What discoveries might lie just beyond the horizon? How will new technologies and missions expand our view of the universe? And what role will MOM Z14 play in shaping the next chapter of cosmic exploration? The journey is far from over, and the most exciting discoveries may still be to come. The future of cosmic exploration is brighter and more mysterious than ever before. The discovery of MOM Z14 has not only challenged our understanding of the early universe, but has also set the stage for a new era of astronomical discovery. As scientists look ahead, they are preparing to deploy an arsenal of new technologies, missions, and strategies, all aimed at answering the questions raised by this enigmatic galaxy and uncovering even deeper secrets of the cosmos. At the forefront is the James Webb Space Telescope, whose mission is just beginning. Webb's unprecedented sensitivity in the infrared allows it to peer further back in time than any previous instrument, capturing the faint glow of galaxies that formed in the universe's first few 100 million years. Over the coming years, Webb will conduct deeper and wider surveys, targeting regions of the sky that may harbor even more massive and ancient galaxies. Each new observation has the potential to rewrite the cosmic timeline, revealing whether MOM Z14 is a rare outlier or part of a vast, hidden population of early giants. But Webb is not alone. The next generation of ground-based telescopes is already under construction. The extremely large telescope in Chile, the 30-meter telescope in Hawaii, and the giant Magellan telescope will boast mirrors many times larger than any in operation today. These behemoths will collect more light, resolve finer details, and enable astronomers to study the structure and composition of distant galaxies with unprecedented clarity. Their adaptive optics systems will correct for the blurring effects of Earth's atmosphere, bringing the sharpness of space-based observations to the ground. Meanwhile, new space missions are on the horizon. The Nancy Grace Roman Space Telescope, set to launch later this decade, will survey vast swaths of the sky in the infrared, searching for the most distant galaxies, mapping dark matter, and probing the expansion of the universe. The European Space Agency's Euclid mission will chart the geometry of the cosmos, shedding light on the nature of dark energy and the growth of structure. Together, these observatories will provide a multi-wavelength, multi-scale view of the universe, allowing scientists to cross-check results and build a more complete picture of cosmic evolution. Technological advances are also transforming the way astronomers analyze data. Machine learning and artificial intelligence are being harnessed to sift through the deluge of information produced by modern telescopes. Algorithms can now identify candidate galaxies, classify their properties, and even flag anomalies that might otherwise go unnoticed. This synergy between human intuition and computational power is accelerating the pace of discovery, making it possible to find objects like MOM Z14 more quickly and efficiently. Theoretical work is keeping pace with these observational advances. Supercomputer simulations are growing ever more sophisticated, incorporating new physics and higher resolution to model the formation and evolution of galaxies in exquisite detail. These simulations are essential for interpreting the data, testing hypotheses, and predicting what astronomers might find as they push further into the unknown. The feedback loop between observation and theory is tighter than ever, with each new discovery prompting refinements in our models and, sometimes, the birth of entirely new ideas. International collaboration is another hallmark of this new era. The scale and complexity of modern astronomy demand cooperation across borders and disciplines. Data from telescopes in different countries are shared openly, and teams of scientists from around the world work together to analyze results and plan future observations. This spirit of collaboration ensures that the search for answers is truly global, drawing on the collective expertise and creativity of the entire scientific community. As these efforts unfold, MOM Z14 will remain a focal point, a benchmark against which new discoveries are measured. Its properties will be compared to those of other ancient galaxies, helping to define the range of what is possible in the early universe. If more galaxies like MOM Z14 are found, the case for revising our theories will grow stronger. If, on the other hand, it remains unique, it will stand as a cosmic oddity, a reminder that the universe is full of surprises. The next decade promises to be a golden age of discovery. With each new telescope, each new mission, and each new insight, we move closer to answering the questions raised by MOM Z14. How did the first galaxies form? What are the true properties of dark matter and dark energy? Are the laws of physics universal, or do they change under extreme conditions? The answers will not only illuminate the distant past, but also shape our understanding of the universe's future and our place within it. In the next section, we'll reflect on the philosophical and existential implications of MOM Z14's discovery. What does it mean for humanity to find a galaxy that should not exist? How does it change our perspective on the cosmos, on science, and on ourselves? The search for knowledge is not just a scientific journey, but a deeply human one, and MOM Z14 invites us to ponder the mysteries that lie at the heart of existence. The discovery of MOM Z14 is not just a triumph of science and technology, it is a profound moment for humanity, one that invites us to reflect on our place in the cosmos and the nature of knowledge itself. When we gaze at a galaxy that should not exist, we are confronted with the limits of our understanding and the boundless potential for discovery. MOM Z14 is a cosmic mirror, reflecting both our achievements and our humility in the face of the universe's mysteries. For centuries, humans have looked to the night sky and wondered about the origins of everything. Each new discovery has expanded our horizons, from the realization that Earth orbits the Sun, to the understanding that our galaxy is but one among billions. The story of MOM Z14 is the latest chapter in this ongoing journey, a reminder that the universe is not static or fully mapped, but alive with surprises that challenge our most basic assumptions. The existence of a galaxy like MOM Z14 forces us to confront the provisional nature of scientific knowledge. Science is not a collection of immutable facts, but a process, a method of inquiry that thrives on questions, doubts, and the willingness to revise our beliefs in light of new evidence. MOM Z14 is a testament to this process. It stands as a challenge to established theories, a prompt for new ideas, and a beacon for future exploration. In its light, we see the power of curiosity and the courage required to embrace the unknown. There is also a deep philosophical resonance to the discovery. MOM Z14's light began its journey across the universe more than 13 billion years ago, long before our planet formed, before life emerged, before humans learned to wonder. That ancient light, captured by a telescope built by our hands, connects us to the earliest moments of cosmic history. It is a bridge across time, a message from an era when the universe was young and the future unwritten. This connection inspires awe, but also a sense of responsibility. As the only known species capable of contemplating the cosmos, we are stewards of a unique perspective. The discoveries we make, the questions we ask, and the knowledge we share are part of a legacy that stretches across generations. MOM Z14 reminds us that the universe is not just a backdrop for human drama, but a vast, dynamic system in which we are both participants and observers. The discovery also invites us to consider the nature of existence itself. If a galaxy can form and thrive in apparent defiance of the rules, what else might be possible? Are there other realms of reality, other laws of physics, other forms of life waiting to be discovered? MOM Z14 is a symbol of the universe's creativity, its capacity to surprise and delight, and its refusal to be confined by our expectations. For many, the story of MOM Z14 is a source of inspiration. It demonstrates the power of collaboration, the value of perseverance, and the rewards of curiosity. It shows that even in an age of advanced technology and sophisticated theory, there is still room for wonder, for moments when the universe reveals something so unexpected that it takes our breath away. At the same time, MOM Z14 is a reminder of our limitations. The more we learn, the more we realize how much remains unknown. Each discovery opens new questions. Each answer leads to deeper mysteries. This is not a cause for despair, but for celebration. The universe is not a puzzle to be solved once and for all, but a story to be explored, a journey without end. In the next section, we'll return to the science, examining how MOM Z14 is influencing the next generation of astronomers and the questions they are asking. How is this discovery shaping research priorities, inspiring new missions, and guiding the search for other cosmic anomalies? The legacy of MOM Z14 is just beginning, and its impact will be felt for decades to come. MOM Z14's impact on the scientific community has been immediate and profound, sparking a wave of new research debate and ambition among astronomers and astrophysicists. The galaxy's existence has become a touchstone for the next generation of cosmic explorers, shaping the questions they ask and the tools they build. In universities, observatories, and research institutes around the world, MOM Z14 is now a case study in the unexpected, a reminder that the universe is always ready to surprise us. One of the most significant effects has been a shift in research priorities. Where once the focus was on confirming the slow, hierarchical growth of galaxies, there is now a surge of interest in rapid, early galaxy formation. Teams are re-examining archival data from Hubble, Spitzer, and ground-based telescopes, searching for overlooked candidates that might resemble MOM Z14. New proposals for Webb observations are being written with an eye toward finding more galaxies at extreme redshifts, and survey strategies are being adjusted to maximize the chances of catching these elusive objects. Theoretical work is also evolving. Graduate students and postdoctoral researchers are diving into simulations, tweaking parameters, and testing new models that might explain how galaxies like MOM Z14 could form so quickly. Some are exploring the role of exotic dark matter, while others are investigating the effects of primordial magnetic fields, cosmic turbulence, or even variations in the laws of physics themselves. The challenge is not just to explain MOM Z14, but to predict what else might be out there, what other anomalies might be waiting to be discovered as our instruments grow more powerful. MOM Z14 has also inspired a new generation of astronomers to think creatively and take risks. The galaxy's discovery is a testament to the value of curiosity-driven research, of looking where others have not, and of questioning assumptions that have gone unchallenged for decades. Young scientists are being encouraged to pursue bold ideas, to design ambitious surveys, and to collaborate across disciplines. The boundaries between observational astronomy, theoretical physics, and computational science are blurring, as teams work together to tackle the biggest questions. The influence of MOM Z14 extends beyond academia. Science communicators, educators, and outreach specialists are using its story to engage the public, to illustrate the excitement of discovery, and to highlight the dynamic, ever-changing nature of science. The galaxy has become a symbol of the unknown, a way to spark wonder in students and inspire the next generation of scientists. Museums and planetariums are incorporating MOM Z14 into exhibits, and its image has appeared in textbooks, documentaries, and news articles around the world. At the same time, MOM Z14 is guiding the design of future missions and instruments. Engineers and mission planners are taking note of the need for even greater sensitivity, resolution, and wavelength coverage. Concepts for next-generation space telescopes, such as the proposed Origins Space Telescope or the Habitable Worlds Observatory, are being shaped by the desire to probe deeper into the cosmic dawn, to find and study galaxies even more distant and enigmatic than MOM Z14. The lessons learned from Webb's success and the challenges of detecting such faint, redshifted objects are informing every aspect of mission design, from mirror size to detector technology to data analysis pipelines. The legacy of MOM Z14 is also one of collaboration. Its discovery was made possible by the combined efforts of scientists, engineers, and institutions around the world. The ongoing study of the galaxy is a model for how international teams can share data expertise, and resources to achieve breakthroughs that would be impossible in isolation. This spirit of cooperation is becoming the norm in astronomy, as the scale and complexity of the questions we face continue to grow. In the next section, we'll explore how Z14 is influencing the search for life and habitable worlds. What does the rapid emergence of complex galaxies mean for the prospects of planets, chemistry, and perhaps even biology in the early universe? Could the conditions that gave rise to Z14 also have set the stage for the first seeds of life? The answers may reshape our understanding of not just where we come from, but where life itself might arise. The discovery of Z14 has profound implications not only for our understanding of galaxies, but also for the search for life and habitable worlds in the universe. If a galaxy of such mass and complexity could form so early, what does that mean for the prospects of planets, chemistry, and even biology in the cosmic dawn? The answers to these questions are beginning to reshape the way scientists think about the origins of life and the conditions necessary for it to emerge. Traditionally, the search for life beyond Earth has focused on relatively mature galaxies, places where multiple generations of stars have lived and died, enriching the interstellar medium with the heavy elements needed to build planets and organic molecules. The assumption was that the earliest galaxies, formed from pristine hydrogen and helium, would be too simple, too chaotic, and too short-lived to support the complex chemistry required for life. But Z14 challenges this view. Its spectrum reveals significant chemical enrichment, with elements like carbon, oxygen, and iron already present in abundance. This suggests that the processes of star birth, death, and enrichment were operating at a furious pace, creating the raw materials for planets far earlier than previously thought possible. If planets could form in galaxies like Z14, then the window for life to arise may have opened much sooner in cosmic history. The presence of heavy elements means that rocky planets, like Earth, could have begun to assemble in the first few 100 million years after the Big Bang. These worlds would have orbited stars that were themselves the products of rapid, successive generations, each contributing to the chemical richness of their environment. The implications are staggering. The universe may have been capable of supporting habitable planets, and perhaps even life, far earlier than anyone imagined. This realization is fueling new lines of research. Astronomers are now searching for exoplanets around the oldest stars in our galaxy, looking for evidence that planet formation is not limited to later epochs. Theoretical models are being updated to account for the rapid enrichment seen in galaxies like Z14, exploring how quickly the building blocks of life could have become available. Astrobiologists are considering what forms life might take in such ancient environments, and whether the conditions for habitability might differ from those on Earth. Z14 also raises questions about the diversity of planetary systems. If the processes that shaped this galaxy were common, then the early universe may have been home to a wide variety of worlds, some familiar, others utterly alien. The intense star formation and frequent supernovae could have created environments rich in energy and chemistry, but also subject to extreme radiation and instability. Life, if it arose, would have faced challenges and opportunities unlike anything seen in the modern universe. The search for biosignatures, chemical signs of life in the atmospheres of exoplanets, is also being influenced by Z14's discovery. Instruments like Webb are capable of analyzing the light from distant planets, searching for molecules like oxygen, methane, and water vapor. If habitable worlds existed in galaxies like Z14, their atmospheres might bear the fingerprints of life. preserved in light that has traveled for billions of years. Detecting such signals would be a monumental achievement, offering a glimpse not just into the origins of life, but into its persistence across cosmic time. The philosophical implications are equally profound. If life could have emerged in the universe's first billion years, then the story of existence is even older and more widespread than we thought. The conditions that gave rise to MOM Z14 may have set the stage for countless other galaxies, stars and planets, each with its own potential for life. The universe, it seems, is not just a place of stars and galaxies, but a vast, unfolding experiment in complexity and possibility. In the next section we'll explore how MOM Z14 is shaping the narrative of cosmic history. How does its discovery change the way we tell the story of the universe, from the Big Bang to the present day? What new chapters are being written, and what old assumptions are being revised? The tale of MOM Z14 is not just a scientific breakthrough, but a new lens through which to view the entire sweep of cosmic evolution. The story of MOM Z14 is rapidly becoming a new chapter in the grand narrative of cosmic history. A chapter that compels us to rethink the sequence of events that shaped the universe from its fiery birth to the present day. For generations, the tale of the cosmos was told as a slow unfolding, a hot, dense beginning, followed by a long dark age, then a gradual emergence of light and structure, as the first stars and galaxies flickered into existence. MOM Z14, however, demands a revision to this script, one that acknowledges a universe capable of astonishing speed, creativity, and complexity almost from the start. In the traditional view, the first few 100 million years after the Big Bang were a time of simplicity and waiting. The universe cooled, neutral atoms formed, and darkness reigned until gravity could slowly gather matter into the first stars. These stars, in turn, began the process of chemical enrichment, seeding the cosmos with the elements needed for planets and life. Galaxies were thought to be small, chaotic, and rare, mere stepping stones on the way to the grand spirals and ellipticals that would dominate later epochs. MOM Z14 shatters this image. Its existence shows that, in at least some corners of the cosmos, the process of galaxy formation was not slow and hesitant, but explosive and efficient. The early universe was not a quiet nursery, but a bustling metropolis with galaxies like MOM Z14 assembling vast masses, forging heavy elements, and igniting waves of star formation at a pace that defies previous models. The cosmic dawn, it turns out, was ablaze with activity, and the seeds of complexity were sown far earlier than anyone had dared to hope. This new narrative is being woven into textbooks, lectures, and documentaries. Scientists are re-examining the timeline of cosmic milestones, the formation of the first stars, the birth of the first black holes, the onset of reionization, and the assembly of the first large-scale structures. Each of these events is now seen through the lens of MOM Z14 and its peers, prompting new questions about the diversity and pace of cosmic evolution. Was MOM Z14 a rare overachiever, or the first of many such galaxies waiting to be found? Did its rapid growth influence the development of its neighbors, or was it shaped by unique conditions in its corner of the cosmic web? The answers to these questions are still emerging, but the impact on our understanding is already profound. The discovery of MOM Z14 has highlighted the importance of looking beyond averages and trends, and of seeking out the exceptions that can rewrite the rules. It has shown that the universe is not a monolithic system, but a tapestry of environments, each with its own history and potential. The cosmic web, with its filaments and nodes, is now seen as a dynamic network where galaxies can grow, interact, and evolve in ways that are only beginning to be understood. MOM Z14's story is also a reminder of the power of observation. For all the elegance of theory and simulation, it is the act of looking, of capturing ancient light and decoding its message that drives science forward. The galaxy's discovery was not predicted by models, but revealed by the patient accumulation of data, the careful analysis of spectra, and the willingness to follow the evidence wherever it leads. In this sense, MOM Z14 is a triumph of both technology and curiosity, a testament to the value of exploration for its own sake. As the narrative of cosmic history continues to evolve, MOM Z14 will remain a touchstone, a symbol of the universe's capacity for surprise, and a challenge to future generations to keep asking bold questions. Its light, traveling across billions of years, is a message from the past, urging us to look deeper, think bigger, and never assume that the story is finished. In the final section, we'll bring together the threads of MOM Z14's legacy. What does this galaxy ultimately teach us about the universe, about science, and about ourselves? How will its discovery shape the questions we ask and the journeys we undertake in the centuries to come? The tale of MOM Z14 is far from over, and its echoes will resonate for as long as we continue to seek answers among the stars. MOM Z14's legacy is already woven into the fabric of scientific discovery, but its true impact will unfold over generations. As we stand at the threshold of a new era in astronomy, this galaxy serves as both a beacon and a challenge. A reminder that the universe is more inventive, more dynamic, and more mysterious than we have ever imagined. Its story is not just about a single object in the distant cosmos, but about the spirit of inquiry that drives humanity to explore, to question, and to dream. At its core, the discovery of MOM Z14 teaches us humility. For all our technological prowess and theoretical sophistication, the universe retains the power to astonish us. Each time we believe we have mapped its boundaries, a new discovery pushes those boundaries outward. MOM Z14 is a testament to the unfinished nature of science, to the idea that every answer is a doorway to deeper questions. It reminds us that the cosmos is not a solved puzzle, but a living, evolving story, one in which we are both authors and readers. This galaxy also embodies the power of collaboration. Its detection and study were made possible by the combined efforts of thousands of people across continents and disciplines. Engineers, scientists, programmers, educators, and communicators all played a role in bringing MOM Z14 into focus. The global nature of this achievement reflects the interconnectedness of modern science, where discoveries are shared, debated, and built upon by a worldwide community, in a world often divided by borders and differences. The quest to understand the universe unites us in a common purpose. MOM Z14's existence challenges us to think differently about the universe's potential. If such complexity and structure could arise so early, what else might be possible? Are there other galaxies, even more massive or more ancient, waiting to be found? Could the laws of physics themselves be more flexible or context-dependent than we have assumed? These questions are not just academic. They shape the design of future telescopes, the direction of research funding, and the aspirations of young scientists who will carry the torch of discovery forward. The galaxy's story also resonates on a personal level. It invites each of us to embrace curiosity, to remain open to surprise, and to find joy in the unknown. The light from MOM Z14 began its journey long before our species existed, yet it now illuminates our understanding and inspires our imagination. In contemplating its origins, we are reminded of our own. The atoms in our bodies were forged in ancient stars. The questions we ask are echoes of a cosmic curiosity that spans eons. We are, in a very real sense, the universe becoming aware of itself. Looking ahead, MOM Z14 will continue to shape the questions we ask and the tools we build. Its discovery has already influenced the priorities of space agencies, the design of new instruments, and the focus of international collaborations. As more galaxies like it are found, or as its uniqueness is confirmed, our models of cosmic evolution will adapt. The search for life, the study of black holes, the quest to understand dark matter and dark energy, all will be informed by the lessons of MOM Z14. But perhaps the most enduring legacy of this galaxy is the sense of wonder it rekindles. In an age when so much seems knowable and mapped, MOM Z14 is a reminder that the universe is still wild, still full of secrets, still capable of inspiring awe. It is a call to keep looking up, to keep asking questions, and to remember that the greatest discoveries often begin with a simple act of noticing something that should not exist. As we close this chapter, the journey is far from over. The universe is vast, and our exploration has only just begun. MOM Z14 will remain a symbol of the unknown, a guidepost for future explorers, and a testament to the enduring power of curiosity. Its light, having traveled across the ages, now illuminates not just the distant past, but the limitless possibilities that lie ahead.